Hi guys, I'm Coach Cowland. In this presentation we're going to look at the physics of sound waves. So sound is formed by the vibration of atoms. These atoms, as they vibrate, they pass their vibration and hence their energy to each other as the sound wave travels through a medium. So how do we go about making noises? Well, it all starts with a vibration of something or another. So in string instruments, it's the strings themselves that vibrate. They pass on their vibrational energy to the nearby air molecules, which pass them on to their neighboring air molecules, and so on and so forth, and that passes on the sound energy. When we speak, as I'm doing now, it's our vocal cords that vibrate and they pass on their vibrational energy to the air within our throats and so on and so forth, just like with the string instruments. In wind and brass instruments, the air is inside a column, and that's caused to vibrate and then amplified by the shape of the instrument. So a sound wave is a compressional or a longitudinal wave. This means that the crests travel in a way parallel to the direction of motion rather than perpendicular to the direction of motion. The molecules are compressed together or they're pulled apart as sound waves pass. So pitch is used to describe the frequency of a sound wave when we're talking in terms of music. And the audible sound wave is from about 20 hertz, that's 20 times a second, to about 20,000 hertz, that's 20,000 waves a second. Frequencies of less than about 20 hertz are called infrasonic, they're very low frequency. Frequencies greater than 20,000 hertz are ultrasonic, they're very high frequencies. Other animals can hear in different ranges. So dog whistles are silent whistles. We can't hear them, but they are ultrasonic. They're very high frequency whistles. The wavelength of sound varies inversely with the frequency. As the frequency increases, the wavelength decreases, as you can see in this table. However, the wave speed through that medium will remain constant. So the equation V equals lambda F, it gives us the velocity of sound through the material. Lambda is, as you remember, the wavelength. F is the frequency, and the speed of sound as it travels through air is about 343 meters per second. As the density and temperature of the mediums change, the speed will also change. The higher the density, the lower the temperature, the higher the speed of sound. So, for example, in water, which is a very high density medium and it's also generally colder than air, the speed of sound is about 1,430 meters a second. If you look at this table here, you can see a number of different media, and I believe that diamond is the highest speed at around about 12,000 meters a second. So, where do sounds travel? Sounds travel anywhere that there is a medium, anywhere that there are atoms and molecules available to pass the sound energy. So, through solids, through liquids, and through gases. They don't travel, however, through a vacuum. So whenever you watch a science fiction movie and there's spaceships flying around and you hear sounds and you hear explosions in space and stuff, this is clearly not realistic because you'd never hear any of these sounds in space. Interference. Now, sound waves usually travel outwards from their source in all directions equally, but sound waves can be reflected and they can bounce off, they can echo. You can get positive interference patterns um, where sound waves collide and make a larger sound wave, or they can cancel each other out and get negative interference patterns. Or the pitch of the sound, the frequency of the sound can change because either the source or the observer could be moving relative to each other. This is called the Doppler effect. So looking at this, on the left we have a situation where The source is stationary, and these rings here represent the wave crests that are traveling out, and you can see that these wave crests are traveling in all directions, and they're equally spaced apart, so their wavelengths are equal, and that means that the sound heard by any observer at any point around here would be exactly the same. Here on the right, the source is moving to the right, and what you can see is that these crests are all piling up on each other, so the wavelength is much shorter. If the wavelength is shorter, the frequency is longer, so you hear a higher pitch here on the on the right of the source than you would here, because over here the crests are being stretched and pulled apart by the motion of the source. So here you'd hear a lower pitch, here you'd hear a higher pitch. So this is the Doppler effect. Now, even though this example gives the motion of the source, the Doppler effect also works if the source is stationary and it's the observer that's moving relative to the source. So when I say relative to the source, I mean either moving closer or moving further away. In either of those scenarios, the Doppler effect would have an impact, and the observer would hear a different pitch than a person standing at the source. The equation for the perceived frequency of the Doppler effect looks a little complicated here. V in this equation is the speed of sound. VO and FO are the observed frequency and velocity, and VS and FS are the source velocity and frequency. So the VS is the velocity of the source. If the source is moving, then Vs is greater than or less than 1. If the observer is moving, then VO is greater than or less than 1. This is the general case of the equation, which means that in certain scenarios VO would just equal 0, and in other cases VS would just equal 0, and that would make the equation a little simpler. Please make a note of this equation. You'll need it in your questions. Okay, thanks for watching.